Hello, my name is Jim Plank. I'm a professor at the University of Tennessee, one of the PIs of TENNLab, and this is a video to help you get started with the TENNLab open source framework for doing neuromorphic computing. Um, so, just as an intro, what this open source framework contains are just a few tools, but with the idea being these few tools can help you do a lot of damage with neuromorphic computing and spiking neural networks. So in this repository, we've got a simulator for a spiking neural network neuroprocessor called RISP. There's a command line tool to help you build, view, and manipulate spiking neural networks. It's another command line tool that lets you load these neural networks onto the RISP simulator and run it, processing inputs, looking at outputs, looking at what's going on in the middle. There's also some information on the guts of the open source software. I'm not going to go through that here. That's more of if you want to rip off the hood and start doing some stuff, that's what's going on there. What I'm going to do here is go through the getting started material that is listed here. It's going to follow this markdown file here, which is in the repo, and then later there'll be a couple more videos for going through some of the main other parts of the open source framework. Okay, so let's begin. We'll go from the beginning. If you're wanting to use this code, let me just also state I'm working on a Macintosh. However, any Unix will work. This has been tested on all flavors of Ubuntu, Raspberry Pi, etc. You don't require any additional software. Pretty much just do your basic download or install of Ubuntu and you're ready to go. Okay, I'll go ahead and clone the repo. And I'll just go to a temporary directory and I'll go ahead and grab the software. Shouldn't take long. No. I've already done this once. And I'm bold enough to do an arm-rf. Okay, nice and quick. And then once you've got it, go ahead, cd into it, and type make, you should be good to go. As I said, you should not have to install any software to get this to work. You should just be able to pull, make, and have everything compile and work for you. There you go. Nice and quick. Okay. Now, the main tools here are these two, the network tool and the processor tool. Again, this is a tool for manipulating neural networks, and this is a tool for running through the neuroprocessor. I also have in the scripts directory a testing script, and it's a good idea for you to go ahead and just do this right now. As soon as you pull and compile, go ahead and run the testing script. You can give it a dash, it'll run all the tests. Let's just say no, so it's not going to keep any files. And it's going to go through a whole battery of tests to make sure that everything's working. Your output should look like this, where it's gone through, done all the tests, and it's passed all the tests, which would be nice. Now, what we're going to do is we're actually going to walk through two of these tests. We're going to walk through this one. We're going to walk through this one. And we're going to go walk through this one. Now, what these are is these beginning tests are all from a paper we wrote years ago. There's our website. Here's how you can find the paper. If you just go to our publications page, search for the word binary, and we've got a paper which was on building neural networks that do binary operations, so and, or, XOR. And we've done this for a bunch of encoding techniques and for processors that have leak or don't have leak. Now, what I'm going to go over here is this network here that does XOR. Now, RISP as a neuroprocessor is super simple. Neurons have activation potentials. You can set their thresholds. Synapses have unit delays. They have weights. And then when a neuron fires, then charge goes out of its synapse. When that charge reaches the next neuron, and it goes ahead and applies the synapse's weight to the activation potential of this post neuron. Now in this XOR network here, all the synapse weights that are black are 1, and the synapse weights that are green are -1. And let me just walk you through how this calculates an XOR. So if these are the input neurons, A and B, here's the output neuron, which is the XOR neuron. If A is 0 or B is 0, it doesn't spike. So you'll notice if A and B are both 0, they don't spike, nothing happens, and this output doesn't spike. If A and B are 1, if either is 1 or both, then it will spike. So let's just look at what happens when both of them spike. So if they're both 1 and they both spike, then they both send synapses, these have delays of 1, with weights of 1 and -1 to the hidden neuron. So those weights cancel and nothing happens. And that happens at both hidden neurons. So nothing happens, the XOR doesn't fire. And that's right, because 1 XOR 1 equals 0. Now look what happens when, for example, just B fires and A doesn't. When just B fires, it's going to send, the synapse is going to have a charge of weight 1 going to this neuron. Nothing comes from A, so this neuron at time step 1 will fire. This synapse has a weight of -1. That's going to go into this neuron, which won't fire. At time step 2 now, we have a fire from this hidden neuron to the output neuron, delay 1. So at time step 2, it will fire. Great, A XOR B equals 1. And same thing happens if it's A is 1 and B is 0. Now, what happens to this hidden neuron that gets the charge of -1, in this network, we assume that the neuroprocessor has leak, and this is a leak mode. RISP supports 2 leak modes, one where you leak all of your charge at every time step if it's non-zero, and one where you retain charge from time step to time step. This network works when you leak all of your charge. So for example, when this -1 weight synapse fires into this neuron, it gets a charge of -1. At the end of the time step, that charge gets leaked back to 0. And that way you can reuse the network. Okay, so hopefully that gives you an idea of a spiking neural network that actually does something non-trivial. Sure, it's a binary operation, and how that works. Okay, so now what we're going to do is we're going to go into our software framework and show how this network works on RISP in the software framework. Now the way I'm going to show this is the test script that we have. Test script 3 does this exact example. So I'm going to run the test script, give it an argument of 3, saying run test script 3, and then I say yes says keep all your temporary files. So that way you can look and see what's going on. Okay. So if I do an ls, you'll see there are a whole bunch of temporary files. Now let me just give you, show you the first one, which is the network. Here, let's make the window bigger. We take a look at it. This is the neural network supported by the software framework. You'll notice it's pretty small. It's 38 lines. It's just text. In fact, it's a JSON. It's garden variety JSON. Very easy to parse, easy to edit if you want to edit it. Okay, and we can just walk through the various parts of this JSON for you to get your bearings with it. Okay, first off, we have nodes and edges. Those are neurons and synapses. You'll note that these map pretty cleanly to this picture. Okay, we have neurons have integer IDs. They don't have to be contiguously numbered, but these are. And you can also give them names, which can be convenient. And then I'll talk about these values in just a second. Similarly, we have the synapses, and the synapses, you can see where they go from. They use the integer IDs, and then they have values, and these values are going to be weight and delay. Okay, synapse values are going to be thresholds. Now, how do I know what they are? Well, if you look up here in the property definitions, this data structure tells you what the neurons and the synapses actually contain. And we do this for flexibility because sometimes you want your neurons to have a whole bunch of things like plasticity or refractory periods, etc. And with this structure, you can have the flexibility of giving your neurons anything you want and then allowing the same data structure to hold them. Importantly here, there's only one property in a neuron, which is its threshold. Okay? And you'll note that's what these numbers are going to correspond to. With synapses, there are two properties, delay and wait, and you'll notice with this index variable, that tells you which one's which. So with index 0, that means the first value is going to be the wait, second value is going to be the delay. Now it's pretty easy to go ahead and match this information to this picture here of the XOR network. Okay, some other things. We specify what the inputs are. These are the neurons that can receive input from the outside world. This is the neuron that will give you the output to the outside world. So that's why we have two input neurons, one output neuron, two hidden neurons. And then lastly, here in this associated data part of the JSON, we have the processor name, neuroprocessor, which is RISP, and then we have the parameters for that neuroprocessor. Now in our software corpus, we have multiple neuroprocessors and each defines its own set of parameters. In this open source library, we're just using the RISP neuroprocessor, but it has a bunch of parameters that you can set so that you can configure your neuroprocessor in a variety of ways. And this is important because with RISP, we have implementations on microcontrollers and on FPGAs, and these settings are important for developing networks for various hardware platforms and to make those networks efficient on the various hardware platforms. Okay, so in this specification, the only thing that's really important is that we do set this leak mode to all, which says that your neurons will leak all of their charge at the end of every time step if they haven't fired. And if they have fired, their charge goes back to 0 anyway. Okay, so that kind of gives you the network. Sorry, I'm just getting my notes going. Okay, good. Now, and I will show you the network tool in a little bit that gives you some software to help you manipulate these JSON files. But what I'm going to do now is I'm going to run the processor tool on this so we can load this network onto a simulated RISC neuroprocessor and then apply some spikes to it and see how it works. So we're going to go ahead and run the processor tool. If you run it with no command line arguments, it just reads from standard in, writes to standard out. If you give it a command line argument, it'll give you a prompt. I often like to just give it a dash if I'm using it interactively, in that way I know what I'm typing and what it's outputting. If you type a question mark into either of these tools, you get a listing of all of the commands, which is useful, but I won't go over it here right now since I know what commands I want. The ML command says basically load a network. This is the network that I just created with my test script, and then from that network it's going to pull those parameters that allow me to create an instance of the RISC processor that's specific to my network, okay? And then it's going to load the network onto that neuroprocessor. So quite a bit gets done in that one command. And it's important to know, because this is an important property of our software, right, that the network stores the processor's parameter settings. So you can use the network to create a processor and then load the network onto that processor, and now you've got the correct processor configuration for that network. Okay, there's an important command called AS that stands for apply spikes. With apply spikes, you can give the command a neuron ID, a spike time, and our times are unit, and a value, and then it's going to queue that spike onto the neuroprocessor so that when you run the neuroprocessor, it will get that input. So let's go ahead and just put a spike let's put it into neuron B. So neuron B is ID 1. We'll go with time 0 with a value of 1. Okay, that's going to cause it to spike. Okay. So now nothing's happened here. I've just queued up the spikes. If I run it, now let me just say I'll run it for 4 time steps. Now I've run the neuroprocessor, it's applied the spike, and then it's run the neuroprocessor. And if I say, for example, an important command, GSR, that says get spike raster, that's going to tell me the spike raster information from the neuroprocessor. So you'll note Neuron 1 did get its spike at time 0. And then when it ran, if we look at this neural network at time 1, this right hidden neuron should spike, which it does. And then at time 2, the output neuron should spike, which it does. Now you'll note I said run 4, and I only have 3 time steps shown here. The way GSR works is that once all the neurons stop firing, it doesn't give you any more information. So in fact, there was a 4th time step, but nothing fired. So it doesn't show you that time step. There are a couple other commands that are useful in the processor tool. If I say OC, that says what was the count of neuron fires during that run call from my output neurons. Here there's only one output neuron, which is neuron 4. It spiked once. If I say OLF, that gives me the time step of the last fire. If I say OT, that will tell me all of the firing times of the output neuron. There's only one here, so that's the reason you only see one. Additionally, there are commands that let you see all of the neurons. So if I say NC, I think it's going to ask me for a Boolean. Yeah, so it says, you want to see everything? Sure, let's see everything. That shows you the count of fires for all the neurons. If we say NLF, that'll give you the last firing times, and you'll note the ones that don't fire, it says they fired at time -1. And then if I say NT, that will give me the same information. It'll give me all the fire times. So these are all useful things for you to use when you're running through simulating the neural network doing an activity. Okay, well, sorry, let me just get back. Okay, good. Now, when you run a testing script, it creates a few things for you. Okay, so it creates the network. It also creates the neuroprocessor params. It pulls that out of that network JSON file. That's a lie. It actually creates it for the network, but it is identical to it. So those are my parameter settings that I use to create the neural network. They do match what's in the network. There's a little more in the network, but that's fine. They're all the same. And then I also have the input of the processor tool that I'm going to give it to do its testing. So in here, it should be slightly familiar to you. I'll go over it. And then here is the output of the processor tool when you run it on that input. So if I run the processor tool and I just give it this input file, then that should match what's in the output file. Now let's walk through this just a little bit to see what's going on. So the ASR command is an apply spike raster command. It's like apply spikes, but instead of giving it specific neurons, times, and charges, you give it a neurons value and then you just give it a string of spikes. And now it's going to convert those into the proper apply spike command. So this will apply a spike at time step 1, and this will apply a spike at time step 3. Okay. Now, what's going on in this is that we're doing basically all 4 input combinations for XOR. So at time 0, I'm applying no spikes to A and B. At time 1, I'm applying to A and not to B. Time 2, I'm applying to B and not to A. And in time 3, I'm applying both of them. So my outputs here should be 0, 1, 1, 0. Now, the output for this neural network comes 2 time steps after the inputs. How do I know that? It's in the paper. Although you could logic it out if you want. So if you take a look at what happens here, so I apply the spikes, I run for 5 time steps, I say, get me the spike raster, and then we look at the spike raster, and this output actually corresponds to what I want. So 2 time steps after the input, so that's going to start here. That's going to be my XOR of 0 and 0. Here's my XOR of 1, 0, my XOR of 0, 1, and then it stopped firing, so there's there's nothing going on out here, but that will correspond to the output of 0 because there's no firing. That means there's 0. Okay, so that's how you can kind of parse through, and you can use the examples to help you, and that's how you can parse through the input, what's going on, and the output. Okay. I'm going to go through a second neural network just so you can, again, kind of go through some of the commands. That network is going to be this network here, this XOR network. Now, this network is a network when there is no leak. So the neurons don't leak their charge at all. And so if you recall, if B fires and A doesn't, then this neuron here, this H neuron, gets a -1 unit of charge. And if there's no leak, it's going to retain that. And if we want to reuse the network, we want it to go back to 0. So these extra 2 synapses make that happen. So when B fires, I'm sorry, when H fires, it's going to send a spike here on this synapse of charge 1. And what happens is that ends up canceling this -1. So this network is basically set up, again, if nothing fires, nothing happens. If both neurons fire, again, nothing happens because each neuron sends a synapse of 1 and -1 to each of these hidden neurons. They cancel, they don't fire. If just one of them fires, for example, B, then this H does fire, and it's going to send that synapse fire with a weight of -1, which is going to cancel the -1 weight that it sent earlier, and that way the A XOR B does fire, but the neural network does get reset, and it can get reused at every time step. Okay. Script 5 generates that network. Okay, so we can look at that network if we want. Right, so same neurons, again, more synapses. We've added 2 extra synapses to the system, and you'll also note that the processor parameter for RISP has set the leak mode to none, meaning we're not going to leak anything, any of these values. That's actually the default of RISP. Okay, and now if we want to run it, let's just go ahead and run the processor tool. Now let's give it a prompt. Okay, we can go ahead and grab the network. We'll do the same thing as we did before. Let's go ahead and put these same spikes in. Let's go ahead and run it 5 time steps, and we do a GSR. Okay. And you'll note the output is pretty much identical. In fact, it is identical to the previous output because it's doing the same thing. The only difference is how it's handling leak, but the output is the same, corresponds to these inputs doing the proper XOR operations. Now let's say we want to see that -1 charge. Okay, so let's go ahead and just put a spike into neuron B. So here, 1, 0, 1. And let's run it for 2 time steps instead of running it for more than that. Okay, if we do our GSR, you'll see, okay, neuron B has fired. That has made this neuron 3, this hidden neuron, fire. So what that also means is that neuron 2 should have received a -1 unit of charge from B, and that should be sitting there in the neuron's potential because it doesn't leak it away. If you say NCH, it will tell you the current charge values of all the neurons. And then you see there it is. There's that -1 sitting there. And if we run for another time step, okay, we can see the output's now fired, and that unit of charge has been canceled by the firing of that synapse. Okay, one last thing before I close this video, and then we'll move to some of the other videos. There's a command called RSC, which is a nice command. Let me go ahead and give you some input first. So here, let's do the same input as before. We'll just put a spike onto neuron B. Now if we say RSC 5, what it does is it's going to do 5 individual run calls. Then it's going to pull out the spike raster information and the neuron charge information and present them to you in a nice tabular format. So now you can see at every time step which neurons have fired, which are these, and then at the end of every time step, what their charge is. So there's that -1 we saw before. So this can be convenient because sometimes doing things one step at a time and correlating what's going on in the neurons and what the firing is difficult. So it's a useful thing to do. Okay, now what you should do next is, now that you've gone through all of this stuff, is you should go ahead and go do this markdown, walk through the markdown file for the network tool, which has its own video. You can watch it much like this one, and then the same thing with RISP. And then at that point, you should be ready to do some damage. Thank you.